Alright, so today we're going to be looking into something that has been brought up a few times on my lithium battery pack videos. So anyway, this whole problem comes about when you're trying to figure out what to use for in terms of cell count for your lithium battery pack. If you're going to use a 3S pack like I did, or if you're going to use a 4S pack in order to create 12 volts, because really the voltage ranges don't quite work out to be within the normal 12 volt standards. Anyway, your dilemma comes with your 3S packs. Go from a voltage range of, at absolute minimum, you can go down to about 2.5 volts or so, which would be 7.5 volts for the entire pack. And the maximum for a 3S pack is 12.6 volts, which is reasonable enough for a 12 volt system. Though you can't, most 12 volt things will not run off of something that's only putting out 7.5 volts. Now, I usually would not take any type of lithium cell below 3 volts per cell. It doesn't matter if it's lithium ion or lithium polymer. Of course, lithium iron phosphate's another story that actually does make 12 volts evenly and almost perfectly, but that's a whole nother battery chemistry. That's a lot more expensive. This is relatively cheap to put together. Now, a 4S pack will run from about 10 volts, which is the correct minimum, though that is the absolute lowest that you can pull the cells down to, 2.5 volts per cell. I do not recommend doing that, though it is possible. And your other issue comes at the high side, because a 4S pack will be at 16.8 volts at its highest voltage, and a lot of the times a power inverter like this will not turn on if the input voltage is over 16. Anyway, this has been suggested a few times, and that would be to put a boost converter in between your battery pack and your load. And it doesn't really matter what the load is as long as it's your 12 volt system. Now, also, a lot of people, I should note this, a lot of people seem to think that a 12 volt system needs to be at like 14 volts. It doesn't. Even if you just let a 12 volt car battery sit with nothing hooked up to it, no charge, no loads, the voltage is going to settle down to somewhere between 12.6 and 12.9-ish, standard lead acid battery. So really, the high side voltage on a 3S pack is just fine, though of course as soon as you put a load on it, it's going to dip down a little bit. Now, you would think that putting a boost converter in line with your battery pack would actually help, because now your inverter has a cutoff voltage of about 10.5 volts, usually 10.5 volts. This one's kind of special in the fact that it actually has a cutoff voltage of about 9.5, so it's a decent bit lower, probably too low for a normal lead acid battery, but it works great for lithium. But anyway, theoretically speaking, you're able to use a boost converter and you can go all the way down to 7.5 volts on your lithium pack and still have, 14 volts coming out of the output of the boost converter going into the power inverter, and you can continue to use the power inverter like that. As I've said in previous videos, once you get down below about 3.5 volts per cell on a lithium battery pack, there's not really that much capacity left in them. Now, you'd think that you're using a boost converter like this would work great, because you're able to pull that 2.5, or pull the batteries down by another 2.5 volts, which should be at least some amount of capacity. But the problem is this thing is an efficiency loss. All right, so essentially what this video is going to answer is, if you put a boost converter like this in between your battery and your load, are you going to use enough capacity out of this battery bank in order to offset the efficiency loss of this boost converter and get more runtime versus just hooking the inverter straight up? And of course, hooking the inverter straight up, it's going to cut off at 10.5 volts or something like that. So anyway, I'm going to go ahead and hook up the test setup. So we have this thing. This is one of these cheap watt meters. This is going to count amp hours and watt hours. These things are honestly kind of a crude measurement device, though it will work good enough for this, and I have some other measuring devices as well. So if I hook that up, you see this meter's got the battery voltage on it. We are at 12.57 volts currently. This thing did just come off of the charger. And then over here we have the voltage and current measuring system. This is based off of an Arduino Leonardo. It has a voltage reference on it, which is just a 2.7 volt Zener diode, and that I've measured it's putting it at about 2.6 volts. So that is being used to calibrate the ADC essentially, because you can't just rely on the 5 volts coming out of a USB port, especially because that voltage can bounce up and down quite a bit. But that ends up being calibration for the voltage measurement, which is just being taken care of by a resistor divider, and this has also been calibrated in code to work very well between about 7 volts and 13 volts. So anyway, it's within a couple of least significant digits when compared to this meter, so you know it's going to be close enough. There might be a bit of voltage drop going through this cable and this meter, but you know it's going to be relative measurements anyway, and we're more interested in seeing what is the difference between this setup here with the boost converter and what the setup is like without the boost converter. So anyhow, we have the setup with the boost converter to start with. This also has one of these ACS 712 boards on it, which I've also I haven't actually had to calibrate the ACS 712 board. I've just checked it for calibration, and it is basically spot on with my other little current meter. But anyhow, coming out of this has been set at about 14.4 volts, I believe. Should be plenty to run this power inverter. This is an ExoVision 300 watt inverter. I think this has been discontinued since I've bought it. But anyway, other than that, this has one of these AC line splitters on it. So I can put the amp clamp around here and we can get efficiency measurements off of it. So that's plugged into the front of the inverter, and then plugged into that is this bulb here, which I believe is 75 watts. But anyway, that is the load, and it's a black light just because it doesn't shove off a whole bunch of light. Anyway, this is plugged into a laptop over here, which is hooked into the serial monitor, or well, the serial monitor is open on the Arduino, and I'm actually going to go ahead and unplug this, close out of the serial monitor, and reset it so that we get the current readings instead of these old ones. And by the way, the code for this has been set up so that it takes 10,000 samples of both voltage and current over the course of about a minute, and then it dumps that, the averages of the voltage and current through the USB cable back into the computer, and it also comes back with a time as well, how many minutes that it's been running for. So what we'll be able to do with the data that's coming off of this thing is take it into a spreadsheet program and actually make voltage and current charts. So that should be kind of interesting to do. Now theoretically, when I turn this inverter on, everything should come to life here, though for whatever reason it doesn't particularly like being hooked up to this boost converter. I don't know if it overshoots or what, but it does not quite like to be turned on like that because the over voltage protection on this inverter is actually being triggered. But if I plug that in now, our little light bulb is turned on, voltage dropped down a bit, and I probably should have let that get the first data point before I plugged it in. But alright, so of course our voltage is going to settle down a little bit. I probably started the test just a little bit too early because I didn't get the initial voltage reading into the computer, unfortunately. I didn't wait long enough for this to get all the averages and stuff, but it'll be alright. We know that it started at 12.6 volts, and I can add in that data point, so it'll be okay. Looks like currently, well, I'll let it settle down. I'll let it get one more data point, and then I'll tell you what the amp draw looks like. Well, according to this, I guess we can look at this one. We are taking about 10 amps from the batteries. This thing's kind of all over the place, though. We are at about 110 watts going or coming out of the battery pack. If we take this meter and we'll measure the amount of current flowing out, and we'll measure the amount of voltage coming out of the inverter. Alright, so that's our current 0.618 amps. And this is a true RMS meter, so it should be just fine for this. So we have 0.618 times whatever the voltage happens to be coming out of the inverter. 127.3, so kind of high. 127.3, so we have about 78 watts going out of the inverter. And I'll go ahead and take this meter and use it to measure the efficiency, I suppose you could say, of this as well. Alright, so just as a reference, we have about 6.3 amps going into the inverter, coming out of that boost converter, and we have about 9.28 coming out of the battery according to this meter. So we actually have 11.6 volts times 9.28 amps. We have about 107 watts coming out of the batteries and about 78 watts going into the light bulb. So 78 divided by 107 is about 72% efficiency for this entire system. And theoretically speaking, we should actually be able to measure the inverter efficiency on its own. That's 6.3. Rough efficiency calculation for this inverter is about 87%, which is pretty good. So let's just say roughly this is 85% efficient and the boost converter is 85% efficient, which is a fairly reasonable number for something like this. We essentially end up with an entire system efficiency of about 70%. So we have a decent bit more wattage going in than what we have coming out. So this is why this may or may not work. It will also drag the battery voltage down faster because we're drawing more current out of the battery. So we might hit 7.5 volts faster than we normally would. Currently we're riding at about 11.5, looks like. According to our Arduino, we are pulling roughly 9 amps out of the battery at 11.55 volts. So yeah, the voltage, 11.50 is the latest update, so that's probably reasonable because that voltage is dropping. And this is the average over a minute, so it makes sense that that is a little bit lower, or a little bit higher, I mean. So anyhow, I'm just gonna let this run until the battery pack gets down to about 7.5 volts, or the boost converter fails to be able to continue to boost this amount of power, because this will have a point where the voltage in the input just isn't enough to be able to boost up 6 amps at 14 volts. So it's going to be running for a decent little while at least. We'll see what it gets down to, and I'll come back to you. So anyway, I'm set up for our next test, which will be without the boost converter. As you can see, basically everything's the same, except now I don't have the converter in line with this, and everything is wired straight into the inverter. Not the best wiring setup, alligator clip and the other wire just kind of smashed in there, but it'll work. So I'm going to go till this inverter stops beeping, which will be something like, or starts to beep, which will be something like 10 volts, 10.5 volts with this inverter. Is kind of a weird one, like I said. But anyway, same voltage and current monitoring setup. Same light bulb, same meter here. We'll go ahead and turn it on. Comes right on when you do that, because there's no like overshoot voltage or whatever it was that was seemed to be preventing this thing from, or seemed to be preventing this inverter from running off of this thing. So anyway, that's going to go ahead and run down. As before, battery goes straight off the charger. We started at 12.55 volts or so. And we're just going to let this run until it dies out on us, just like before. Alright, so I've brought the data here into a Google spreadsheet just because that's what I have to work with. But anyway, over here is the data from our original experiment with the boost converter, and then this is the data from the second experiment without the boost converter. Now, these are kind of interesting results. So first off, when we used the boost converter, we pulled about 10 amp hours out of the battery. And when we didn't use the boost converter, we pulled about 8.5 or so amp hours out of the battery. So we did pull more capacity out with the boost converter, but as I had kind of predicted, if you come down here and you look for where the current drops off at, this over here is the number of minutes, this is the current, this is the voltage. So anyway, With the boost converter, we ran that load for 66 minutes, and without the boost converter, we ran the load for 71 minutes. 70 or 71, somewhere in there, it got shut off. So without the boost converter, we actually ran for an extra 5 minutes, even though we didn't pull as much capacity out of the batteries. Now, there were some interesting things happening here, especially with the boost converter. We'll look at the voltage without the boost converter first, because this is kind of the characteristic lithium-ion battery discharge curve, except for it didn't go all the way down to the 0 or 2.5 volts cell, whatever it is. All right, so first off, looking at this is the voltage and the amperage coming out of the batteries without using a boost converter. So pretty typical. You start off, 12.6 or whatever, and then it's you turn the load on, and then it slowly kind of decreases. And right here, the load got shut off, and the voltage kind of recovered. So anyway, this is the current the entire time. So it started off up here at about 6.7 amps, and then it just kind of slowly decreased. And it slowly decreased because we were driving a resistive load on the output, and the inverter's regulation is not that great, so the voltage dropped a little bit as the battery voltage was dropping. That's not a big deal. It's just how this is, and we got a little bit less power out. And if you look at it, this is the voltage discharge only, the voltage drop only. I'm not really sure what this is, the 0.99 in the red is, because it's not even showing up on here. But anyway, yeah, the bottom axis is time, and then time in minutes. And then the other ones are whatever they say they are. All right, so anyway, looking at the voltage is pretty much what you expect. There's a little glitch right in there. I'm not sure what that is. Actually, there's a couple of those little glitches along that graph. Now, that's what you would expect for what happens without a boost converter. With the boost converter, we have some interesting graphs going on here. First off, this is the current, right? The red is the current. And it shoots up at the start about 9 amps, and then it slowly increases, which is what you expect because you have a constant power going out of the boost converter. So when the voltage on the input drops, you need to have more current going into it. But what's interesting about this is that it comes up and it comes up, and eventually what happens is it starts to, well, it drops off rather rapidly, and you see the voltage comes back up along with the current. Now, what has happened here is the boost converter, it didn't quite like something that happened in this voltage range right in here, this, well, let's see, about 9.4 volts maybe, somewhere in there it started to come up. 9.17 is the lowest there. But what it actually did is when I first set it, we were at about 14.3 or 14.4 volts. And when it got around to here, the output voltage of the boost converter dropped down to about 14.1. So still above 14 volts, but not what I set it to. It dropped a little bit, and it actually started making a bit of an audible sort of 60 hertz hum, like the inverter was injecting noise back into the boost converter. But anyway, after that happened, the current actually dropped off pretty significantly. We were up at 12.35, and it came back down to 10 amps. And then as the voltage dropped more and more, it actually shot back up. And then right in here, the boost converter dropped out completely. That was at 8.65 volts, so not quite the minimum, the absolute minimum that you theoretically should have been able to take it to, which would have been 7 volt or 7.5 volts. So anyway, the boost converter, I shouldn't say completely dropped out. It was still outputting like 10.5 or something like that, but the inverter was starting to complain about low voltage, so I went ahead and shut it off at 8.65. And at that point, like I said, we pulled about 10 amp hours out of the battery pack. And I shut it off there, and then the voltage recovered. And the other thing I wanted to point out about this is the voltage on both cases. Well, with the boost converter, the voltage actually did recover all the way back to 11.02. And without the boost converter, we recovered to 11.4 almost. So yeah, there is still more capacity for sure left in the batteries in both instances, which is kind of interesting. And then we have this weird looking discharge curve. Again, there's these little glitches in it. I'm not sure if that very well could be the inverter adjusting a little bit, so it starts to draw a little bit more current in order to get more voltage on the output. It very well could be some kind of weird thing in the test setup. Could be anything. That one's about 11.1. Let's see if it does it at the same. 11.5, so they're not at the same. Then again, on this one, the inverter shouldn't have been adjusting for anything because it should have had a good solid 14.3 volts or so. But anyway, this graph is basically just a bit of a zoomed in version of the blue one on here. And it does show, toward the end, you get this, the typical lithium ion discharge curve where it just starts going straight down. Sadly, this didn't give me the curve that I really wanted, and I did run this test twice, by the way, to make sure it wasn't some weird anomaly with the test setup, and it did the same thing twice, so yeah, it's not actually an issue with the test setup or anything. Well, it's the boost converter, really, is what it is. It's causing this kind of weird act. So you probably can't really get a boost converter that's even powerful enough. I'll go look at the specs here in a second. But what I did want to talk about is it's going to make a bit of a difference what the output load is, whether or not this actually affects it. Like, this was a 60 watt light bulb or something like that. It's been a while. I haven't had time to shoot this segment of the video. This spreadsheet's just been sitting on here for a while, but anyhow. Alright, so this is the boost converter that I use. It is a Drox 600 watt 12 amp DC boost converter, voltage converter, 12 to 60 volts to 12 to 80 volt step up power supply transformer module, regulator controller, constant volt amp car. Okay, whatever, anyway. $21 boost converter. And if you look kind of into the specifications here, we have 600 watts, which I'll talk a little bit about that in a minute, but you have input and output voltage number 1 is 12 to 60 volts, which is a default. Now I had this set on the input output voltage 2, which there is a jumper. You can see that it says in choice on it right where my cursor's at. You should be able to see that right by the capacitor on the bigger image there. It says in choice on it, but anyway, that is a 9 to 16 volt input, which looking at the silk screen, it looks more like it says 8 to 16 volts, but it's kind of hard to read, so we'll just say it's 9 to 16 volts. And it even tells you, it says 4.3 lithium battery and 12 volt battery. Please do not overrange, so don't put too much voltage into it when it's like that. And also we have maximum input current is 16 amps. So we weren't going over 16 amps, and it does tell you if it's over 10 amps to use or to enhance the heat dissipation by adding a cooling fan. Now you may say, well, we were getting up to 12 amps, maybe that was why it dropped out. Well, this thing actually did have the fan from the inverter blowing right across it, and it didn't get all that hot. So anyway, and then your output voltage range is 12 to 80 volts, which is continuously adjustable. But anyway, the next point that I wanted to bring up is this says it's a 600 watt module. Now that's probably a 600 watt module at 12 amps and a relatively high voltage. If you note, this 12 amps is the maximum output current, 16 amps is the maximum input current. So anyway, when it comes down to it, this 12 amp limit kind of limits the amount of current or amount of wattage that you can actually get out of it. So when you're talking about something that you're running at 14 volts, like what we did here, 14 times 12 is only 144 watts. So putting a boost converter like this would, significantly limit your output power. And from what I can see, there might be some bigger boost converters, though usually the higher the current you have, the harder it is to get one to run down at a lower voltage. Like this one already is only running down to 9 volts. Now over here there's actually one that claims to be a 900 watt unit, but if you look at it, it's not really any better. We have 15 amps apparently available to us instead of 12, so this one's going to be a little bit better. Let's see, 15 times 14 is going to be 210 watts available at a 12 volt, well, 12-ish volt output. So that one's a little bit better, and this is actually one of these fancy numerical ones. I believe that that's 12 amps. or yeah, maximum 15 amps on the output. Yeah, that's right. I don't know about the input. But this one, where's the, so DC 8 to 60 volts in, I'm assuming. So this might actually work a little bit better than the one that I have. But that 900 watt one, I'm not sure you can get one any bigger than that. And really, you might not even want to search for the wattage. You might just focus on how many amps that it can handle, because that's pretty much what you're going to be limited by in this case using your 12 volt appliances. But yeah, anyway. Also, another thing, I did have the current limit turned up to the max, so it should have been able to output 15 amps. Instead, we only got 12 at the max, and then it dropped off. I'm assuming we only got 12 because it kind of got down to the lowest voltage it can handle. Like this is about 9 volts, it's only rated at 9 volts, so it kind of eased off on the output voltage, which lowered the current in turn, and it brought the voltage back up, and then eventually it kind of did the same thing again, and it eventually completely dropped out at 8.65 volts. So the boost converter, I mean, it did what it said it should do. But as I said, this is going to be an efficiency loss for sure. How much of an efficiency loss this may actually require some more investigation as well. I might have to do the same test with, you know, this is actually probably pushing the amount of current that I can push out of it already, because we got up to 12 amps. I'm imagining, you know, even if you went to a 100 watt light bulb, you might be pushing that 15 amp limit that we have on this boost converter. Now, in conclusion, this probably actually requires at least one more test. It probably needs to have a test at an output load of something like 20 watts, something lower anyway. I can't even push this setup that much higher. You can almost do one more test with a higher load, but we have to remember we can only pull 16 amps through the input, and we're already pulling 12, and we're only running 60 watts or so on the output. So now, in conclusion, this probably needs at least one more experiment where I take this exact same setup and I run it at a lower current, lower output wattage, maybe 20 watts or so. I can't go a whole lot higher than the 60 watts that we were pulling, because we have a 16 amp limit on the boost converter, and we were already pulling, what, 12.3 according to that. So I can't push a whole lot more current out of it, but I can go lower for sure. And I'm not entirely sure if putting the boost converter on a lower wattage would it help it or hurt it. Because on one hand, you are pulling the batteries down a little bit lower, actually quite a bit lower, 8.6 versus 10 point something. As I also mentioned though, as you get down into the sort of 3.5 volts per cell range, there's not really that much left in them, and I actually might have to go and take just a resistor or something, constant current load. Anyway, probably not a resistor, probably some kind of constant current load, and just get the discharge current graph, the characteristic discharge graph of my particular batteries, because this graph ends kind of short and this one's all wonky because we pull different amounts of current throughout the graph. So I may have to just do something like that. Now, anyhow, I may actually do another video and test this same exact thing at a lower current, so 20 watts instead of the 60 or so, which will take quite a while to drain the batteries, but might be worth seeing if that helps it or hurts it, because the efficiency loss over that amount of time might actually add up to a bit, well, quite a bit more than the capacity gain that you would get from coming down to the lower voltage. Now, granted, you can't go all the way down to the 7.5 with this particular boost converter anyway. There's probably stuff out there that would do better than what I have. I'm just working with the equipment that I have to experiment with. But anyway, interesting results. At least at this particular load with this particular battery bank, putting a boost converter in hurts it just a little bit. 65 minutes of runtime versus 70 or so minutes of runtime, 70, 71. So adding the boost converter, at least in this particular circumstance, under the exact amount of load that I had and the same battery capacity, adding the boost converter decreases the runtime by about 5 or 6 minutes. That is not a huge difference, though. You're also putting extra strain on your batteries by doing this. You're draining them down a decent bit further. So, like I said, you're losing runtime in this particular instance by using the boost converter versus not using the boost converter. So I'm not going to say it proves anything because we haven't done a whole heck of a lot of testing. Really, to do this right, you need to test it at various loads. This test, I'm going to say, is probably the higher end of the load that you could put through a boost converter anyway. So anyway, hopefully you guys found that useful, and well, that's about it for now, guys. I might do another video testing this on a lower load, but that's about all I have for now. So see you next time, guys. Bye.